some code. In here we'll be solving binary tree level order traversal. Level order traversal means we'll be seeing 3, then we'll be seeing 9 and 20, then we'll be seeing 15 and 7 level by level. Pretty straightforward. This is typical breadth first search style problem where we'll be adding the binary tree to our queue and then removing it from queue and assigning it to our list. So that's how we can see it level by level. Let's jump into coding. So first thing first, if root becomes null, then we'll just need to return the empty list. So let's define our list. So returning result right away, which is empty. Let's create our queue, which will hold 3 nodes. I like to use deck for creating queue, stacks, linked list, double linked list. It provides some methods where we can remove first, remove last, add first, add last. So let's add to our queue given binary tree root, and so we have our queue now contains this binary tree, and we'll just need to traverse it until queue is not empty. So if queue is not empty, we'll be traversing it. When it's empty, it stops. So now we need to see this traverse it by its levels. So we need to find a way to see how many nodes we need to traverse it in a given level. So for that, we can get that information from our queue size. So first time when we add it in here, the given root, then the size is 1, so we are seeing this 3. Next time it will become 2, then we'll traverse it one by one in here. So let's start seeing nodes in a given level. And then we'll be removing it from our queue. So in queue it's first in, first out, so we add it to the last, then we're removing it from first. Now, in this example, we are seeing 3. What we are going to do is collect all those nodes in our array. So we can create another array where its sole purpose of that array is to collect level nodes. And then in each iteration, when we're moving to a different level, then it gets reset. And then in the end, we'll be just adding this level list to our result. So now we have a level list. We will collect our given node. Well, now our level list contains 3. So in the end, we'll just add this result level list to our result. And so Now, as you can see, let me just return for now. Now, in our level list, it contains 3, and 3 was added to result. Then Q becomes empty here. And how do we proceed with the next levels? So in order to proceed with the next levels, while we were, because like when we see node 3, we have an access to its left and right. And that's how we can actually keep adding to our queue. So we will say if so for a given node we have ability to see left side. So if left side is not null, because like it can become null, like when it's at 9, the left side becomes null, so we don't need to add it to our queue, because like we can just stop it there, and then not stop it there, add it to while when we don't add to our queue, eventually our queue becomes empty. Then this will break out of this loop. So if left side is not empty, then we are adding our queue. Same goes with the right side. So first iteration, 3 was removed from here. It was added to our list. Then it was added to the result. Now our result contains 3. On the second time, so here Q, we added 2 nodes to our queue, left side and right side. Now size becomes 2. When we are coming to here, this becomes true because queue is not empty. We have 2 nodes in there, and level size becomes 2. So we are seeing it again. We are adding in here, removing 9, adding it to our list, and when we're checking the left side and right side, we're not adding anything. So queue size is 1 now, because it was 2, this was removed, now it stays 1. And then we are iterating again. We're seeing 20 and we're removing 20. We are adding to our list. Then we're checking left side and right side. Those are not null. Then we are updating our queue with this 15 and 7. So we removed 20. At this point, queue size became 0. At here, now queue size is 2. Then we are again iterating, coming to here and seeing this 15. Now again removing it 15, adding it to our list, and then left and right side is null, so we're not adding anything. Queue size is 1. Then again removing this 7. Now queue size became 0. Left side and right side are nulls, so we're not adding to our queue, and queue becomes empty. Then we just stop our while loop and return our result. So let's run our code. Now return result. Submit it. So time complexity in this problem is O of n, where n is all nodes in given binary tree, because we're seeing it all those nodes. And the space complexity is O of n, where we are holding in our queues all these nodes.